Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And our goal is to improve OOR program locality. Here is just one example. For SpecJVM Java-C benchmarks, we run it on a simulator using 8K L1, DL1, 8K instruction L1, and 128K L2. This is the original performance in total cycles. And we found if we have a perfect L2 cache, which means there's no L2 cache misses, we can improve performance by 20%. And if we use both perfect L1 caches, if there's no L1 cache misses, we can improve another 20%. This is just a graph to show like how much space we can improve if we can improve the program locality. And back to OOR program, there are two observations. We found memory managers can reorder objects at runtime during the garbage collection. And so we can change the reordering policies to improve locality by changing the object layout. And next, I'm going to introduce our online object reordering algorithm. So to improve locality, we want to first find out where are the cache misses. Here's the memory access graph for DB, one of the JVM benchmarks. And we separate the accesses by access to different part of the heap. Like boot image is basically the VM objects, and the stack accesses and the large object accesses are the second bar. And we use a generational collector, so we have access to the older generation and to the nursery. And we found although the stack got the most memory accesses, got the highest bar, but the older generation got most of the cache misses.
So what kind of architecture are you dealing with? It doesn't have any code misses at all?
Actually, for the current implementation of the jython we are using, the code is part of the heap.
No, not code. So
you mean composite?
The first time you access memory, is there
right.
a cache miss or no?
Yes, it's a cache miss.
Okay.
So those are counted among the misses here?
Yes.
Okay. So there are misses in the boot image, it's just that they're so few.
Yes, you cannot see like the numbers, but there are misses. And like for other benchmarks in SpecJVM, it got the same trend, but it may vary a little bit. But it's always true that older generation got the most cache misses. So we focus our target on improving the older generation locality. And it's actually easier to improve the older generation if we use a copying collector. We can just reorder objects while promoting objects from the nursery to the older generation. And traditionally, most VM use a class oblivious traversal order, which is just go depth first or breadth first when traversing each class. Or sometimes it uses some variation of depth first or breadth first traversal order. Or we can use a class-based or even instance-based object reordering. And how to traverse by different type of class or by just different instance of the class. We can use static profiling to collect the information, or we can use dynamic sampling to collect the information. And for our algorithms, we use online algorithms, so we need to do a dynamic sampling. So to collect information for the runtime reordering, we can collect information at runtime, say using a read barrier to intercept every read to the object fields. But that could be very expensive. Or we can use static analysis during the compilation. But it requires very expensive, and it's really hard to predict field accesses at runtime just by static analysis. So our algorithm is to combine those two using both static analysis and runtime information. So the goal is to have very low overhead estimation. So the static compiler analysis we use is very simple. First, we exclude the code basic blocks from the method. And then second, we just getting the field access information in the rest of the basic blocks. And the second step is using adaptive sampling to identify hot method at runtime. And most VM can do that. And we estimate the hot field accesses to be field accesses in the hot method. And this is very low overhead because the adaptive sampling is already in most of VM, and the compiler analysis is very simple, straightforward. Here's an example. Saying we have method foo, and the compiler look at method foo, and it found this normal basic block to be hot basic block, so it collects the field access information, A.B. And for the exceptional handling, it considers it to be a very cold basic block. So it ignores the field access in that basic block, and it creates an access list for method foo, which includes A.B. And for the adaptive sampling, if it already got food access list, and the adaptive sampling found out foo is a hot method, it will look up in foo's field accesses and find out and consider A.B access to be hot, and record in the class A state structure. And after we find the hot field, the next step is how we traverse it. If we have like 1, 4, 4, 7, and 2, 6 to be hot field, we traverse like this. We traverse 1 and look at all its children and find a hot field to 4, and 4 has hot field to 7. And then we start traversing the rest of the field for 1. And we traverse 2, and 2 has a hot field to 6. And then we traverse the rest. And we consider object to be hot, either it has a hot field like 1 or 2, or it's pointed by a hot field like 6, 7. And we allocate those hot objects into a separate space. So inside memory, we can see we allocate 1, 4, 7, 2, 6 in the hot space, and 3, 5 in the cold space. So the overview, there are 4 steps. We first record object accesses in each method, and then we find out hot method by adaptive sampling, and we combine those two information and find the hot field accesses, and reordering the hot field in the garbage collection when we copy object to the order generation. And we also copy the hot object into a separate space.
So if you are instrumenting the hot methods and instrumenting all the hot basic blocks, how's that much cheaper than instrumenting everything?
we are not instrumenting hot. You mean recording the field access?
Yeah.
It's a lot cheaper because, like, when we use jython, there's very few hot methods during the run. Like, there are hundreds of methods being executed at runtime, only like 10, like 20 methods considered to be hot. So it's a lot fewer information we need to record.
So it saves on space, but what about time? It's like if they're hot, then you're going to be visiting them frequently.
If they account for 90% of the execution time, then we're not instrumenting 10% of it.
Are we actually instrumenting the code?
No. I'm not instrumenting the code. Yeah. We only record it when we optimize that method. And after we record, we just put it aside. We never look at it during the execution. So it doesn't increase the runtime overhead. It just increases a little bit of overhead at compilation.
So you know the hot methods because your adaptive compiler also wants to know that anyway, so you know what to compile. That's basically what it is. You're already identifying what the hot methods are to do a better optimization.
Right. And actually, my next animation can show more clearly where I add the code. Like for the original VM, it takes the Java source code and use baseline compiler and generate executing code. And adaptive sampling look at executing code and find hot method and send to optimizing compiler, generating optimizing code to improve the code quality. And at the same time, the garbage collection, if it's using a copying collector, it copy object affect locality, but we don't know whether it's good or bad. And here's our OOR algorithm. During the optimizing compilation, we add entries into the access info database, which associate with each method. And in the adaptive sampling, after it found a hot method, we look up in the database. If we found there's access information for that method, we will record those field accesses in the class state structure. And during garbage collection, we use those hot field advice to direct the field reordering. Yes, it's class-based.
So why do you need to know about naming the fields? Isn't in the end you're just going to allocate objects of the same class in a specific place, so you don't really need to know what fields are hot, as long as the object itself is hot. Is that right?
Right. We are class-based, so we don't remember individual instance of the class. Actually, string doesn't. The string basically has two fields. Yes, it could be like some class, like some instance of class has one hot field and the other instance has another hot field. Yes. And currently the OR doesn't deal with like the same class have different hot fields. But if those hot fields are in different phases of the program execution, we do decaying and for the hot field. So we can detect the phase changes and do adjustment. But if it's interleaving, then we can't do anything from OR. Okay. We also change garbage collection copying orders. And next, I will show some experimental results. First, I will introduce the methodology we do our experiments. We use jython, which is the VM written in Java. It's high performance comparable to the commercial VMs. And it uses a timer-based adaptive sampling and dynamic optimization for the hot method. For our experiments, we use pseudo-adaptive, which basically making the program more determined by telling the program which method to optimize and optimize to which level, so that we can generate the same code for each run and get more deterministic result. And we use second iteration, which exclude the compilation overhead. Because like Eckhout's paper, it shows that if we measure the first iteration, the compiler activities will dominate the performance. And for the memory manager, we use MMTK, which is the infrastructure, has a collection of allocators and collectors. And it's very easy to do comparison between different policies of memory management. And it has multi-space heap, like it has boot image for the VM objects, it has large object space, and it has immoral space for object it considered the immoral never died. And we use a generational copying collector with 4 meg nursery. And here's the result. This table shows the cost of using OOR without, and this column is using OOR, but not the last step. So we do all the collecting information and the compiler analysis, but we don't do the reordering. And this is the original default configuration. And this is the difference. Actually, we using OOR, the overhead only is actually slightly better. This is actually the 0.19 is within the noise of the execution. So it just shows that overhead OOR is not detectable from our experiment. It basically has negligible overhead.
So what are those numbers measuring? Is higher better or lower?
And this is the absolute time in seconds.
The lower is better.
Yes.
So it's actually faster to use OOR?
Yeah, to use OOR without doing reordering is actually 0.19 faster.
Is there any reason?
This is just the noise of the experiment. It's not.
So there's so little overhead that there's no way to measure it.
Right.
Okay.
And the next performance. This is the performance of DB, one of the JVM benchmarks. You can see we use 3 static traversal order, depth first, breadth first, and partial depth first, which is basically doing depth first for the first 2 children. For the only goes depth of 4, and for the rest of the children, it's doing breadth first. So it's basically generating a hierarchical depth first, and we found it has very good performance in our previous experiments. So we add this traversal order. And we found for DB, breadth first has really bad performance. And for the rest of benchmark, for the rest of traversal order, it's basically on top of each other, and all are being one of the best. And here the y-axis is just different heap sizes the program is running on.
So let's see, so using OOR, how does that affect the traversal order? It's basically, what traversal order, I mean, it seems like they're orthogonal. I said OOR is going to put things in a different place. But what traversal order are you going to use this in?
But when it put object in different space, it also changed the object within that space, changed order within that space.
But it's not going to change it logically. Still gonna, so I guess so it actually changes the traversal order when the garbage collector runs?
Yes, it traverses the hot field first.
Oh, I see, okay. You didn't, okay, I understand.
And this is performance jython. Jython is an open source Python interpreter written in Java. It's a much larger program compared to the JVM 98 benchmark. And you can see before the partial depth first was one of the best, and now it's one of the worst. And OOR is 20% better than the partial depth first. And the depth first is about 3–4% worse than the OOR. This just shows the variation of different static traversal orders for different benchmarks. And OOR stays as one of the best. But we found for most of benchmarks, okay.
In the OOR scheme, do you have any specific traversal order among the hot fields to take some temporal?
And for the hot field, we don't have orders. If it has two hot fields, we just like which one we see first, we choose that one. Okay. But we can, because we record different hot fields, like with different temperature. Basically, we can't do like the hottest first, but we didn't do it in this experiment. And we found for most of the benchmarks, it's not very sensitive to the traversal order. It looks like javac, like the best and the worst doesn't have much difference. It's 1 or 2% difference. And for those benchmarks, OOR stays among one of the best, or it could be like 2–3% worse than the best performance.
So is all of the folks coming with the cache?
And yes, we do hardware performance counter, and I found most of the performance difference are from the cache difference. Yeah. And it's actually very interesting because we run those experiments on Pentium 4, and Pentium 4 is using a trace cache as instruction cache. And for sometimes trace cache has very interesting property. Like if you write within 1K range of the trace cache of the current executing code, it will flush the whole trace cache. So there's pathological cases like you can trigger to make one program has really disaster performance just by triggering that feature. And but the performance result I showed here doesn't have that effect because we can measure the number of trace cache flushes. And yes. Yeah, they're not significant different among those different traversal orders. Maybe the program is not big enough. I would assume that if it's big enough, it got more impact on the TLB. And related work, actually there are lots of research has been done for improved program locality. Like at the very beginning, there are lots of research done on improving array access inside loop for C or Fortran benchmarks. And there are also studies for all programs using different kind of static reordering. By Wilson et al., we found hierarchical depth first traversal being the best. And Chilimpi et al. Also did a lot of research on this area. It did some static profiling to collect hot field information and get good performance. It also has instance-based object reordering at runtime. But this work is done on C shell using a read barrier. The read barrier overhead in their paper is about 6%, and for our work, we found like to have 6% overhead is really hard to overcome to get, because for most benchmark, it's not very sensitive to different traversal orders. So to conclude my talk, the static traversal orders can have up to 25% variation in their performance. But OOR always improves or matches the best performance among different traversal orders, and it has very low overhead. Any questions? And among the benchmarks, I definitely saw they use hash maps in the benchmark, but I don't know how intensive they were using hash table. Yeah. In that case, the instance-based traversal order can improve. If you always access the same entry in the hash table.
So I guess there's two separate things going on. Maybe maybe I'm not quite understanding, but so there's the idea that there's a layout idea where you're putting objects that have a particular class that are hot together.
Right.
And then there's the traversal order where you're visiting objects in a particular, when you do the collections in a particular order. So can you separate those two? Can you run the experiment where you do the layout and you don't affect the traversal order, or not do the layout and do the traversal order independent?
Actually, we didn't do much about the layout in the sense of we only change the layout objects if they are connected to each other. So we only do the different layout during the traversal. So we cannot do like just pick this instance and put it in the memory here.
Okay. And the other question I had was, how much cost is there to determine, at runtime, if you're in the garbage collector, to determine how do you actually determine which are the hot fields to traverse? Is there some kind of flag or something that says?
Yes, there's a flag in the class state structure.
For each field, basically says?
Yeah.
So if there's more than one hot field, is there any difference between only marking one field as hot or marking all the hot fields as hot?
If you mark one field is hot.
Yeah. So assume you have a class that has, let's say, 3 hot fields, and if you limit your marking scheme to only marking one of them as hot, do you see any performance difference between that and marking all 3 of them as hot? Because there will really only be one object that is co-located, as in located next to that object.
Right.
But then you'll have to retrieve whatever is reachable from the first hot object, and then somewhere else you will have the following hot reachable graphs.
We didn't do that comparison, but if one field is not hot, it will be copied into a code space, which is far away from the current object. We would think that probably will occupy more pages for the hot objects.
So that made me think, are you actually visiting each object twice? Once for tracing the hot objects, and once for tracing the cold objects? Or
No, we just in one traversal.
You traverse the hot ones first,
And
then the cold ones.
No, we traverse like all the fields, like with code. Oh, I traverse the heart first, and then traverse the code. Right?
But it's all in one bit. Oh, there are two queues. Okay. Okay.
Yeah.
Okay.
You mentioned that you didn't choosing basis of the program, so how does that work? Because the optimizing compiler doesn't have the same instrumentation.
Right. The only use of the optimizing compiler for OR is to figure out which field is accessing. And for different phase changes, we can see, because usually if the phase change happens, there's one more limitation in the phase change. If accessing different field of the same object happens in one method, we couldn't figure out which one is hard. If it happens in two methods, like one method accessing the second field, the other access the seventh field, and we can see phase changes depending on currently which method is hard. Yeah, it happens when we say currently we found the method accessing the second field to be hard. We will mark the second field to be hard and decay the rest of the field if it was marked before. And actually, I have results for doing that. It's just one synthetic benchmark I use to test our experiment. Here is the OR with phase change, and here's without phase change. That's like about 30% improvement we can get. This is the default depth first, which is way worse if it doesn't have any idea which field is hard.
Okay. So Long's going to be around during the day, and if somebody who isn't already on the schedule wants to talk to him, let me know after we talk here and go. Thanks a lot. Appreciate it.
Thank you.
Right. Yeah. I sort of got that, but yeah. Okay. Yeah. I mean, it's yeah. When go down that pointer. Right. And yeah, I didn't understand about the two queues. I think that was something that there were. I think if I were to do the talk, I would say more about the mechanism because So have an example and a worked out example of how you have five objects connected, and,
right.
And here's the hot fields and here's the cold fields, and this is how we. Because the fact that you have the two queues, I mean, you have this. What? There has to be.
Well, there could be two destination areas, and there would actually be different behavior.
Right. It's actually the same queue but different destination.
Are you doing depth first or breadth first? I mean, in some sense, if you're only going to traverse the hot fields, then you're leaving behind objects whose cold fields you haven't traversed yet. So they have to go somewhere, right?
Right.
So there has to be two queues, it seems to me. Or two destinations. I mean, it's the same thing when you're copying.
I think there are two destinations.
Right.
Set of pseudo threads for the different.
Right.
How the
yeah, I mean, the destination that's sort of basically the equivalent of these squares.
No, they're different, and there's very subtle interactions because assume you traverse a cold field in an object that is in your hot space.
Right, which you will.
It could be, since it's a cold field, you will be copying the destination to the cold space.
Right.
But that object could be hot reachable from another object.
Yeah, I see what you're saying. Right.
Which
Right, but
is-
it's
which
the
is-
same thing with the queues, right? I mean,
No, the queues would actually do get the hot reachable objects in one area, and only the things that are not reachable by hot fields and hot objects